In my backpack.
Okay, so we are going to finish chapter 5 today, and then we will do the lab. Alright, so in chapter 5 so far we studied gases. Just remind you those different gas laws, and we call them two types of gas law. Right? Boyle's law, Charles' law, and Avogadro law. So you have that Boyle's law is P1 times V1 equals P2 times V2, and this is one law. The second law is you can either write either one on the top. So volume over temperature, volume over temperature. This is Charles' law. And then Avogadro law is one, like something volume with more for that thing. So these three laws are the individuals. And in gas, you have that four variables. Just remember, you have that four variables P, V, and N, and T. Okay? So these three laws are only two variables innate. If the other two variables not innate, that means they are constant. So for these four laws, the unit except T in Kelvins, and the pressure can be any units as long as you have the pressure for P1 same as the pressure for P2. So then the other law is the ideal. Ideal gas law has all those four variables innate. Pressure times volume equals N times R times T. And obviously we have one extra letter called R. R is not a variable, R is the constant. Because R is a constant, you need to know what the number for R. So R usually, in the first few sections, you see R equals this number, 0.08206, and has unit APM times liter divided by mole divided by Kelvin. So that means when you use this equation solving some programs, conveniently, you just use ATM for pressure, liter for volume, and mole for N, and Kelvin for temperature. So that is about what we studied in the first few sections. Those are the main points, the main equations. And we also studied like Tuesday about density. We say D equals pressure times the molar mass divided by R and T. And this equation is coming from that equation just by some simple algebra rearrangement. So therefore you will use the same unit, and R still here, so R will be 0.8206. Temperature in Kelvin, pressure in ATM, and this capital M is the molar mass, which means the typical unit gram per mole. And once you have those units put in, you get the unit for D is the gram per liter. Alright, so from this equation we also know how to calculate the molar mass. Obviously, if you know those informations, and if you know density for a given gas sample, and if you know the pressure for that gas sample, you know the temperature for the gas sample, you can calculate what is the molar mass. So then the last section we learned Tuesday is about the gas mixture. So when we have gas mixture, and for each component, you can still use this equation, okay? Because we studied those gas is kind of ideal gas, which means there are no attractions. So no matter what gas you have, you put them together, like the gas in the air, so pretty much you can treat in all those different gas in the air equivalently. Just think about it as one type of gas. And so therefore we study those partial pressures and partial pressures so we studied the Dalton partial pressures. You can use this equation to calculate what is the pressure for one particular component, and that will depend on how much that particular component you have. Because we know in the gas mixture we will have the same volume, same temperature, so we don't have to specify a particular volume for one particular component in the gas mixture. We don't have to specify the particular temperature for one particular component in the gas mixture. We only need to specify what is the particular partial pressure for one particular component and what is the particular amount of N for that particular component. So that's what we studied so far on Tuesday. And obviously, if you know what is the mole for, like, let's say, what is the mole in this room is air, what is the mole for N2, and if you measure the volume of this whole room, which is weight, if you measure the temperature of this room, and you measure the pressure, you obviously know the pressure. So therefore you can calculate and what is the number of N, and vice versa. If you know like how much, what I try to say is so that's I would say what I try to say is that if you know the number of N and you know that volume and temperature, you can calculate what is the pressure, what is the partial pressure of N2. Vice versa, if you know you can somehow figure out what is the partial pressure of N2. You can calculate what is the number of mole of N2. Alright, so now today we are, before we finish this this talking like Tuesday, we also talk about another way to find out the partial pressures. So that is this way. So we call that partial pressure of some components. For example, in this mixture we have H2 and O2, right? So we have this mixture, and you have a partial pressure for each component. So let's call the partial pressure for helium is helium. So now what we studied the last section of Tuesday's class is so this partial pressure. Pressure of helium in that component, and we use this notation called PHE. Right? And the last equation we studied Tuesday is the mole fraction of that, then times the P total. So this is the sort of mole fraction of helium. Alright, and again you can still use that last method. You can still use the ideal gas equation. You can still use P helium times weight like the same gas for all the same volume for all the gas, and that equals N helium and times R times T. So that is this one way, this is the second way. Obviously depends on how much information you know. If you know the mole fractions of helium, you know the total pressures, you just use that equation. Otherwise, if you don't know like what is the total pressure and what other information for other components, but you just know like how much more of helium do you have, right? And obviously, if you only know this, it's difficult to find that out. To find that out, you have to know like the total moles. Right? So depending on what information you have, right? All right. So let's say for this for this problem, and then you see like what you given is you will have enough information to use either way. So therefore, depend on what you like and what you remember on the at the time you solve the problem. I probably want to use the first way. I use the first equation because we already know how to use the second equation. Alright? So let's keep that in mind. Let's you want to first solve that equation, solve the problem called find out the mole fraction. Alright, mole fraction, again called the x. And let's see x, we have these two gas, and helium oxygen mixture, we have two components. And we will call that mole fraction of helium. And that will equals mole of helium divided by mole of helium plus mole of oxygen gas. Alright, so that is the definition, and that's the problem. You want to find out the mole fraction, you just see what is the equation for mole fraction. Right, and then the mole fraction of oxygen has like two ways to find that out. Okay? You can use the same way you use for this for helium. If you only have two gas, two components, and or you can use that equals 1 minus mole fraction of helium. So use either one, you can find the mole fraction of oxygen, because if you have two components, all the mole fraction for all the components adding together so equal to 1. So this second equation depends on what I said. All the mole fractions adding together equal to 1, which means if you have x helium and you have x O2, and adding together should equal to 1. If you have 3, and if you have x helium and x oxygen, and if you also have some of those nitrogen gas, and that also adding equal to 1, depending on what kind of mixture you have. So therefore, if you want to find out the mole fractions, you have in a different way. Depending on what you like. Use that equations, probably you will have less mistake, because use this equation depending on what you get for the first one. If you make a mistake for the first one, then you get both wrong. Alright, so let's use the initial definitions to get both of them. So I will delete this one. Right, so now obviously you want to find the mole fraction for the gas, you need to know the mole for all the gas. And which is so important, as I said before, at the beginning of this class, mole to gram to mole conversions is so basic. It pretty much become like your alphabet for your chemistry class. Right, so you have 24.2 grams of helium, and when we start in the first few seconds, you want to get more from the gram, and think about use molar mass, right? The molar mass of helium, just very simple formula, He, because helium is noble gas, not a diatomic, not like triatomic, and you have 4.00. Right, so I'll just write 4.00 gram of helium and 1 mole of helium. So I hope by now everyone knows this step, even when you are swimming. Kind of like you learn a language, because when you learn a language, you can dream in that language, and you are doing that language. 22.4 divided by 4, and you get 6.05 mole of helium. Right, so similar story, you get mole of O2 will equals the mass of O2. And I just read carefully the mass of O2 referring to what O2, O3, O1, or O2. So in this form we have O2. And then just examine that O2, and O is 16, and O2 that means you have 2O. So therefore you have that molar mass is 32.0 gram of O2 and 1 mole of O2. Right. So you have 4.32 divided by 32, and you get 0.135 more. So this is more of O2. Understand? So now, once you get those information, and which will be very straightforward, you just apply in. So you have more fraction of helium will equals more of helium. So this is helium, and then the total more, which means 6.05 plus 0.135. And actually all those more will come out because this also has more, this has also more, and right. So those more will come out. So I just deleted those units. So more fraction is very similar. Mass percent has no unit. Right. So you get more fraction of 1 program. 6.05 divided by 6.05 plus 0.135, you get 0.978. Right. And so then I'll do the same calculation for more fraction of oxygen gas, and just switch the numerators. The denominator is still the same, because the denominator representing the total more. So we have 0.135 divided by 0.135 plus 6.05, and you get 0.0218. Adding those together, you probably not will get exactly 1 because those are the numerical errors. But principally, this one plus this one for equal to 1. Alright, so once you get the more fractions, and if I want to use that equation to calculate the partial pressure, for example, partial pressure of helium for equals more fraction of helium times P total. So I said I want to use that equation because we already know how to use the other equation to get the partial pressures. The other equation is P helium equals N helium times RT divided by V total. So you can use that one. You can also use that one. And that one you already know how to use it. So let's start with this one. So obviously to use this one, you already have this number here, 0.978. You need that number. Now as I said, all those gases will behave as one gas. You want to get the P total. The P total will very similar as that equation. So that will equals N total, which means all of the gas together, no matter more of helium, more of O2, so just call them more, and times RT divided by V. Right. So obviously you need those informations. You need the N total, which means. So let me write here. A total will equals N helium plus N O2, that will equals 0.135, but not matching. So if I write that underneath that, so that is 6.05 plus 0.135. So now it's this is more of helium, that's more of O2. You get 6.185, so that's our N total. Once you find out the N total, you just apply to the equation. So you have 6.185, and R, as I said before, so in the first few sections, you pretty much use this number a lot. And what are our temperature? Temperature in Kelvins, then already in Kelvin, that's good. So 298. And you don't have to see the temperature for helium and temperature for oxygen because the gas mixture, every gas has the same temperature. And then the volume will have the same volume. What our volume is 12.5 liters, so that's our volume. Well, I don't have any units, so I will just also dealing with that unit. Alright, so you just do the calculation and get the P total. Once you get the P total, and use that, get the partial pressure. 6.185 times 0.0203 times 298 divided by 12.5. Right? So you get 12.10. And as you know, if you use those right units, if you use liter for volume, and if you use Kelvin for temperature, if you use this number for R, and your pressure for the ATM. Alright, so now let's put it into this equation and get the partial pressure of helium. Alright, so you have this small fraction, 0.978, and then you have this total pressure is 12, let's multiply 12.10, and ATM. This guy, unitless, have no units, and this is ATM, so therefore you get ATM for the pressure, which makes sense. 12.1 times 0.978. So you get 11.83 ATM. This, we call that P helium, which is the partial pressure of helium. Right? And so then how can you find out the partial pressure of oxygen? Again, there are many different ways. Right? So tell me one way to find out the partial pressure of oxygen, of the O2 gas. What do you think? Which way you want to use? Many different ways. Right now I think about probably 3 or 4 ways.
Total minus the BA.
Yeah, you can do that. Yeah. So that you can take the total minus that. Can I do that? Okay. Because Dalton's partial pressure law. That tell you. The partial pressure law tell you if you have P helium plus PO2, that will equals P total. Okay? And now you already know two numbers. P total is 12.10, and P helium is 11.83. Then plus PO2 is one we don't know. So as Barretta said, you just subtracting the total from by the partial pressure of helium. Right? So 12.1 minus 11.83, and that gives us the partial pressure of O2 equals 12.10 minus 11.83, and that equals 0.27 ATM. Alright, so that's, and what other way to find out the partial pressure of oxygen gas? Well, you can use the ideal gas law, right? Because you already know the mole of, we just read that, we know the mole of O2, right? So like Maggie said, if you want to use ideal gas law, you want to find the partial pressure of O2, just write P O2 will equals NO2 times R times T divided by V, and T and V are the same for all the components. And if you remember what is mole of O2, just apply mole of O2 right here, right? I think that is 0.1 something, right? Mole of O2, and I just apply the same number 0.08206, and the temperature is same for all the temperature. For all the components. And the volume should be also all the same. So our volume is 12.5. what other way you can think to find the the partial pressure of O2? You can use density, right? You can use density probably. And what else you can use? How did we find the more fraction partial pressure of helium? Huh?
Mole fraction times the total pressure.
Okay, I think that's good. So that's another way, and so I think that's about this example, right? All right. Now you do a practice. I think this practice probably not that much difference. Answer. Okay, so what are you going to use? Are you going to use like the ideal gas law to find out the total pressure? Right. So the pressure, you cannot use the ideal gas law, right? Because use ideal gas law to find the total pressure, as what we did for one problem, is you need the total. You need the total mole, and those kind of information. So think about what equation you're going to use to find the total pressure. Not that difficult. Just think about it like in your mind. What equation has something to do with the partial pressure? I mean the total pressure, right? The total pressure you can use ideal gas, and you can use what else? What else equation has the total pressure in it? Okay, so what do we find? Anyone get some like idea what equation you use? Oh, you use that equation I write on board there too, right? Yeah. Probably that's I said the ideal gas law. Probably difficult to use that one, right? Can you use this one to find the total pressure? Can you use that P total equals N total times RT divided by V? Can you use this one to find the P total? No, you don't know the information, you don't know what temperature that's good too. You don't know the volume, you don't give to you. You don't know what is the N total either. Right. So I said, you think about what else equation has that P total in it. So yeah, so you can use a similar equation like that, right? Where I mean the partial pressure equals more fraction times the total pressure. You can do the problem, you not ask you to calculate the partial pressure, but the partial pressure is already given to you. What do you say?
Is it D?
It's D.
The answer is D, right? The answer is D. So what you use, you use, so this, so it's again about that helix mixture, what it means you have helium plus O2 mixture. So you have this mixture, right? And so now you have the mole fraction of something. What mole fraction do you know? Oxygen, which means X mole fraction max O2 equals 0.035. What else information do we know? The partial pressure of oxygen PO2 equals 0.21 ATM, right? So if you summarize like what we know, obviously we don't have enough information to use that P weight equals NRT because we don't know the temperature and so on, right? And I think are there any equation that has total pressure in it? Yeah, so then that's the new equation we learned just in Tuesday's class, which is about this is PO2 equals XO2 times P total. Right, so then you just substitute every numbers in this equation, you know you get 0.21 ATM on the left side, and you get 0.035 have no unit, and then times that P total, which is the one you want to find out. And out from a very simple problem, right? And you find out the P total, just divide 0.035 divide by 0.035 out, and then you take 2.21, right? Divide by 0.035, and that will give you. So this will give you what? 6. Alright, so that's this practice. Right. Now there are some other usefulness about that Dalton's partial pressure law. Which means if you doing some of those in some of those study or in work and or in research, you do something like you get some of those gas, and you want to measure how much gas do you get. So one way to collecting the gas is collecting gas over water. By the so-called water displacement. So in this picture tell you those are the chemical reactions in that test tube, and we will produce some gas. So you just use some guiding line and let the gas come out and go to this beaker. The beaker initially filled with gas. So once the gas come out, and that will push out the water, so you're collecting the gas on the top of water. So that's good. You can measure how much volume you collected and what is the temperature of the gas. And then you can use those gas law, like the ideal gas law, to calculate that. But the problem is, in that ideal gas law, you need to know the temperature, volume, and pressure to get the mole of particular gas. Right. So one particular problem for those kind of measurements, you can measure the volume very easy because usually you can use a cylinder that has the scale in it, like the burette. You can read how much gas you collected. You can measure the temperature by just plugging a thermometer, see what is the temperature of the room temperature. So the room temperature is pretty much the same as the temperature of the air or of the gas. The problem is to measure the pressure. You can measure the pressure. Let's see, we can measure the pressure of the air, and the pressure of the air will be same for everywhere. So therefore, the pressure of the air will be same on the surface of this container, this bottle container, because the air is in contact with this surface, but air is not in contact with that surface. So by doing some of those addition subtractions, so as this picture shows, if you draw a line here, like what we did for that manometer problem at the beginning of this chapter 5, so every like body of liquid and at the same depth, you have the same pressure. So if I draw, so that means this is our surface. And you can see that's the surface. Now let me extend that surface all the way to this container. And then you will see this is the same depth. So even though for this part is on the surface, for that part is under some liquid, but it's the same depth. so-called the same depth. Understand that? So according to like some of those physics law, for like the same continuous liquid, no matter what is the shape, you do like circles or just very simple like a swimming pool, at the same depth, and you will have the same pressure. This pressure we know that is very simple. There is no liquid on top, only the air on the top. Understand? So here, this pressure here, we call that P air. And I think in one problem we studied, we also call that P18N. You can like go to the Google channel, see what is this pressure, and then we'll tell you the pressure on the surface. And then this part here, this pressure here, we call that P. Well, what we did for the manometer problem, now this, if we call this is our P, well, I probably confuse you. I call that P total. The P total will be the gas total pressure on the surface of that liquid. So it's not really a total, it's a subtotal. It's a smaller total, not really the total total. Right? So then this pressure here, not only that P total, but this pressure referring to the pressure right here. So imagine if you measure the pressure there, you not only have the pressure from that P total, the so-called P total. What else will give the pressure if you measure the pressure here? If you measure the pressure here, okay, we have that gas. Well, there's a gas mixture that will give you some pressure. Okay. And what else will give you pressure if you measure the pressure here? It's liquid. We call that a manometer, the pH. Right. So you can call this P here or equals pH, pH plus what we write on the top called P total. Right, now for this problem, and you just know like you can use that equation and find out the P total. Okay? You can find out the P total. Okay? How can you find the P total? Well, you see this P equals this P here, because this two arrow. Okay? Let's use that. So this arrow here, and this P here, okay, that will equals that P. Why that equals that P? Because they are in the same depth. Right? So once you measure or you go Google find out the P air, that will equal that part, and then you measure what is this liquid, so you can convert it into the same unit, you get this part. So therefore you just subtracting that one by this one and get this one. Now that is not a problem. Okay? What is interesting to us is what we collected. What we collected is, for example, for this here is this gas, H2. Okay? Now here, this P total not only comes from the H2, not only comes from the H2. So this P total has what altogether gives us the P total. So this P total equals what? We have one gas here is H2. What else gas is in this part of this container? Huh? H2. How do you know that is H2? Water vapor. What always can vaporize? Yeah, so that's it. So you have that. If you have that gas, you know you generally get some gas. You call that H2, right? Then plus pH2. The pH2 that's easy to measure too. And you can use a table. You just measure the temperature for this liquid water. Approximately, we probably have some solution here, and will depend on whether we have pure water or not. I think we'll have pure water, so you find out those tables is pretty much kind of precise. So once you find out the temperature for water, and you will find out, use the table, you find out what the pressure of that water vapor at that temperature. You already know this number, so therefore you do subtraction and get the pH2. Well, so I added one step here because we will do one lab later on, and we need to use those kind of information. So you will see this step is not on the lab notes I give to you, but later on in the lab you will need that. So that's what is important for right now for this section. Okay? So this total here. So this what I said total again here. Okay? So this is the total pressure here, which means the pressure in that gas mixture. You know that's not really easy to identify that is a gas mixture because you don't know there's also a gas water vapor. You know that you're collecting H2. Right. So let's keep that in mind. Okay? Collecting gas often by having them display water from the containers, that's what we saw before. And the problem is that since water evaporates, so there is also water vapor in the collected gas. And then the partial pressure, because what we saw in the previous those calculations, you want to calculate what is the mole, right? So like partial pressure of O2, okay, it connected to the mole of O2. Okay? So if you want to find out how much some particular gas you use or some particular gas you produce, and obviously you need to know not only the total pressure and also the partial pressure for some particular gas. Right? So the water vapor problem is not a very problem because you can measure the temperature of the water and use the table to find out the right way. Just don't forget, okay, if you're collecting gas over water and you always have the water vapor, you want to find out the partial pressure of the gas you produce, or sort of the dry gas pressure, which means the partial pressure of the gas you produce, just by subtracting. You can see the table for the water vapors, so that pretty much, well here we use Celsius, because this is not a calculation. But when you do the calculation, and you want to use the PV equal to nRT, you make sure your temperature should be in kelvins. Right, so now let's see this problem. So in order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant was collected over water at a temperature 293 Kelvin and a total pressure of 755.2 millimeter mercury over a specific time period. So you have a total volume too. You just measure what is the total volume. Then you want to find out what mass of oxygen gas in gram was produced, right? And so you will read those questions carefully, see what it gives you and what you want to find out, and either going from forward way, which means from what it gives you going forward, from backward way, which means you're starting from what you want to find out. So let's see what we want to find out is the mass of oxygen gas, right? So we're starting with that, we're going like a backward way doing our plan, right? We know gas, I mean gram and I think in this class I give it out many times. So you have the gram and mole is kind of connected. So when you think about it, you want to ask the gram or mass, you think about that in the density you can also get mass. And also more often you are thinking about mole. Right. So then this is about gas. So it depends on what you know. If you want to find out solutions more, you can use molarity and volume, right? For gas, we study in this chapter, so you pretty much you have to use. I'm going to put that in the quotation mark. Use that PV equal to nRT, or you can use Avogadro's law. think about it, because we studied like two law has a more innate, and the other one is V1 over N1 equals V2 over N2. Which one can you use? And obviously you don't have enough information to use Avogadro, that even though that also has more innate, right? Right, so therefore you think about use the first one, use the ideal gas. Right? And then you will do continuous. You can use the ideal gas and see what do you need. Right? So what do you need? Let's say you need the pressure, you need the volume, and you need the temperature. Right? And obviously you need to remember what is R. So after you study those gas mixtures, so therefore you not only need to know the pressure, you need to be more precise. So the pressure is for what? And obviously I just say the pressure. If you know the total pressure, you know the more pressure, you can find the total pressure, right? But here, everything here is about O2. So if you put that substance in, you want to find the O2, so you want to find more O2. Right? I find more O2 in this equation, so this will be the O2 here, and this N will be referring to more O2. You don't have to put a subscript for the volume and the temperature, because every gas in the mixture will have the same volume and same temperature. Right? So therefore, we adding up, we want to find these few numbers. We want to need the partial pressure of O2, the volume of this oxygen gas, which is pretty much the same as the gas mixture, and then the temperature of this gas mixture. Right. So what do you think? Can you find out the partial pressure of O2? And so how can we find the partial pressure of O2 now? So we know we collected this gas mixture, this gas over water, so therefore we will use that P total equals P O2 plus P H2O. Everybody agree? Right? I think that is the one way to solve the problem using formulas. So you probably have a lot of formulas. Just think about which formula has the variable or the quantity you want to find out. So then obviously one equation that has that partial pressure of O2 in it is this Dalton's partial pressure law. Right? So we have the total pressure. So right now you don't have to convert. Okay? You don't have to convert because you are only do the subtraction and addition. Okay? So this is the total pressure. Do you agree? What is the partial pressure of O2? We don't know, right? So we have P O2. Can we find out the partial pressure of water vapor? I give you the table, so that means depend on the temperature. The temperature given to you is about Kelvin. You just do a subtraction, right? So give you 293 Kelvin. This table is in Celsius. So what number are we looking for? 20. So 20 right here. Right? So we will have this number here. So which means 17.55. So that's our strategy. So we said, what number we need to think about what equation have that number or have that quantity in it. Right? You do subtraction, and so you get 755.2 minus 7.55. Okay, so we get 737.65 equals P02. Right, now once you have this information, and so our procedure is, our thinking process is like this. We want to use this ideal gas equation, we want to find this N, we already found out this numbers, so therefore you have to think about, sometimes even straightforward. What is the weight and what is temperature? So those probably is easy, but make sure you get into the right unit. All right. So that's about it. So now let's just simply going forward now. So we have those informations. And we want to find out. We want to use this P02 times weight equals N O2 times R times T. Find this guy. Right. And either way, you can just get an equation for this guy by yourself. So let's do that. I think you did pretty good. Like Tuesday, so just take this times this divided by R and T. That will give you NO2 very clearly. Right. So once you decide you use this equation, and just make sure in this equation you cannot use arbitrary units for the pressure or the volume, because that's depends on the number you use for R. Okay? So pressure should be ATM, and the volume should be liter, and you don't have to see the volume of O2 because we have to get mixture or everyone has the same volume. Right. So we have that pressure of O2 from our last calculation because okay, just remind you, it's very careful. So in this equation, your pressure should be ATM, right? So we start with 737.65, which is a millimeter mercury. I will write or the so-called torque. So sometimes these two units are the same. So if I write 737.65 mmHg, or I can write TORR, torque. Right, so what you do, just take that equation and divide by 760, and then this will come out. Or sometimes you will write this number in this unit in it, so those are the same. So yes, that's the same. So 0.971 ATM. So now you get that number, right? Which is the part of pressure of O2. Okay. Now let's substitute here. So 0.971. Right? And what is our volume? 1.02 is our volume in liters. Okay. And if you use those ATM in liters, then you know the number for R is 0.08206. And temperature should be in kelvins, right? We have 293. Right. 0.971 times 1.02 divided by 0.8206 divided by 293. So that is 0.0412 more of O2. You agree? So now the problem is to find out the mass. Once you find the problem of O2, and how you find the mass? More mass, right? So I'll write here the 0.0412 more of O2. And now what molar mass shall we use? Shall we use molar mass of O? No, because we have that O2, right? So therefore you will just like for every 1 mole of O2, and then you have 32.0 gram of O2. Okay. So if I put this in this format, I put the 32 on top, and the mole at the bottom, and this whole fraction comes from molar mass, right? And then you can see this comes out. Right? So that's similar, but those are very like basic calculations. So make sure you don't forget that. And you get 1.32 gram of O2, and that will be your final answer. that's what you did. Right, now do a CRE, so they're very similar practice, but just collecting different gas. Okay? So I change the picture a little bit, and we collecting the so-called acetylene. Acetylene is also a very important organic gas. Has this formula C2H2. C2H2. Two numbers are very close. I think A and B are very close, right? Well, what's the answer? Anybody find some answer? The B? Very similar as the problem we did, the example we did. So what you do is you want to find the mole, right? So think about you want to get the mole, right? So in this class, what chapter has something to do with mole? What has something to do with mole? Think about all that something has to do with mole. Let's see, what can contain the mole? Mole containing what? Gram, right? Do you know the gram? No, right? What else has something to do with mole? Ideal gas law. PV equals nRT, so that's N mole. What else has mole in it? Molarity, the capital M. Okay? Yeah. So these few just in your mind quickly, and obviously which one has something more to do with for this problem. Are you going to use think about how much mass you have to get more? You don't have the mass of that, right? Do you know the molarities? I guess probably think about the gas law, right? Right. So therefore we're going to think about this equation, right? Now this equation. If you have a pure gas, you just use the total pressure and the total moles for the gas mixture. Think about those partial pressures and that particular mole, right? Yeah. So that's good. So therefore, you just think about P V and R and T. Well, you want to find out that mole of acetylene. So that is C2 and H2. So that will be that equation. So therefore you will have NC2 and H2. Right. So this acetylene here is C2 and H2 has that formula. You can use that name called the acetylene, right? But you can just call that a P. C2H2, and that is the gas. Right? So therefore you cannot use the total. Right? So here this number and we have that P total equals 758. Now here we use the torque. Yes, so then you will see this p total, okay, this number is given. This number is given from the problem. Now you use the Dalton's law, you know that PC2H2 plus PH2O equals 758, 4. So then another problem is, you know this number, so you have this is the so-called PH2O. So PH2 right now is millimeter Hg. Millimeter Hg, as I write here, is the same. I will use that. It's the same as torr. So therefore, so this equals 17.55 torr. Because they are the same unit. It's similar, very similar as the milliliter. 1 milliliter equals 1 cm cubic. So if I give you some volume, like in this example, if I write 500 ml, and you just can write that into 500 cm cubic. Okay. All right. So therefore, you will have this C2H2 plus 17.55. For the torr equals 758 torr. Okay. So then you just do a subtraction, right? And you find out what is C2H2. All right. So let's. Do you think we need probably just add one step, right? So you have that PC2H2 equals 758 minus 17.55, that will give some number, right? Right. So let's say 758 minus 17.55, because 740.5. Any questions? What do we do next? We want to use what equation now? This equation, right? This equation here. You want to find this number, right? And use this equation, and you already know everything. You know this guy now have this number. And what is our volume? 500 ml. What is our temperature? 293 from 20 degrees Celsius. Okay? So make sure you get the right unit. Right? Right. So let me just erase some of those and make sure everyone gets the similar steps. Right. So we first need to convert this. Right? Convert this into what unit? ADM. Right? So we'll start with 740.5 torr, okay, and 760 torr, 1 ADM. Understand? Right? If you want to use that equation, make sure you have to use R. If you use R, that means your preferable ADM for that number, right? So 740.5 divided by 760, you get 0.974 ADM. You get the same number? Okay, good. So then, what about the volume? Can you use milliliter? Can you use milliliter for this problem? No, what do you do? Okay. So let's do that. So we have 500, so this is our weight. We see weight equals 500 ml. Right? So now we know for every 1,000 ml, there's 1 m. Right? Well, 500.0, so that's, so you have to be careful with this. That's what we're studying in the term 1, 6 figures. So ml comes out, right? you get 0.5123 3 zeros because you have to keep all those significant figures. Right, so one number here, one number here. So this is that is a difficult problem because all those not the numbers not really in the right unit. You got unit, right? So you have temperature equals 20 upon 0, and level equals 20 upon 0 plus 273, and you get 293 kelvins. Now you have everything in the right unit. Right, I think that's it, right? What do you do next? Just substitute the numbers. So you have a pattern here, put it here, right? So that's a finish the problem. See if you like. Okay, so I'm going to erase all those numbers we prepared. Okay. Right. So I want to say like N is the mole, right? C2H2 equals, right? And 0.974. That's our pressure. Okay. Times 0.5000. That's our volume. Divided by 0.08206. That's our R. Okay. Divided by our temperature, which is 293. That's our Kelvin temperature. Right? So that's how you get that B, right? So 0.974 times 0.5 divided by 0.08206 and 293. You get 0.02025, right? Right, so you want to 0.0203, which has a unit more. Right. Right, now let's do something different, like difficult. Okay? That means you are going to use what we just did so far and get more, okay, from all those informations, and repeating some of those steps what we did in Chapter-4. Okay? So the principle of reaction is stoichiometry from Chapter-4. Can be combined with the gas law for reaction involving gases. What is like one very important step in Chapter-4 you learn? That what we learned that in Chapter-4 we learned some other stuff. That's what we call that reaction stoichiometry. It's about quantity conversion in chemical reactions. What do you think is the most important step in that Chapter-4 about those quantity calculations? Very good. That's you have a balance equation. Once you balance equation, what are you going to use in the from the balance equation? More ratios or the coefficient. Okay? Both sides right. So the important step in Chapter-4, I think, is about that more ratios. Okay? Okay? So this step I emphasize at the bottom here. Okay? More A to more B. You already learned how to calculate more A. More A like more of copper atom, copper anions, okay? Or more of water, okay? From Chapter-2, Chapter-3, but just take the gram divided by the molar mass, right? Now in Chapter-4, what you learn is convert. Different convert. That means you don't have to know the gram of B. If you know, like you can produce B from A, right? So that's what Maggie said. If you know those equations, you know the balance equation, and you can convert and use some more ratios. So this step, so if I write here, what do we use? Is sort of more ratios. Most of the time, we use more ratios. So then you can call them more ratio or molecular ratios, depending on the problem. Sometimes you probably don't use more, just use moleculars. Huh? because those coefficients have two units, either molecular or mole. So numerically they are the same. If you get a mole ratio 1 to 1, that means you have 1 mole and 1 mole. And that also understand as 1 molecular, 1 molecular. Right? Mole ratio is very important. Okay? Okay. Well, so where you get the mole ratio? Where you get the mole ratios? When we talk about it in the reaction stoichiometry, where you get the mole ratios? Balance equation. Where is the balance equation? Balance equation is what? Okay. Very good. So these are mole ratios from coefficients, okay, of balance equation. Okay. That is the important part in Chapter 4. Okay? That's the important part in Chapter 4. So once you have that, and you just combine everything together, it's just a pretty much a learning process, right? So once you remember, you can convert from A to B. Or A may be gas, B may be gas. Or A may be like solid or liquid. So depending on what kind of information you have. If you have a solid, you probably just use more mass and a gram, right? You find out more. Okay? If A is a gas, okay, then most conveniently you can get more of gas by the gas law. And gas law, as we emphasize again, two types. Either the ideal gas law or those Boyle's Charles, depending on what kind of problem gives you. So once you have those gas law and you find out the mole of A, and then you just use mole ratios and get the mole of B. And then you can use the mole of B to do something else. It depends on what is the state of B. Now for this chapter, because we are studying gas, so therefore we think about B is also gas. And if B is also gas, if you know the mole of gas B, and if you know some other information, if you know the temperature and the pressure, you can find out the volume. And vice versa. Yeah, any of those you can, if you know the pressure and the volume, you can find the temperature. Right. So that is about these few steps. Some of those are still like similar. So you have that one important step. Any questions? And so then in particular, if you talk about a gas at one particular condition called STP, and your calculation can be simpler. But otherwise, you probably have to use Avogadro's law or ideal gas law to find out more, right? If I tell you your gas is at STP, then you remember STP is standing for what? Standard temperature and pressure. What are the numbers for the so-called standard temperature is what temperature? Yeah, 273 Kelvin or 0 degrees Celsius, right? What is the so-called standard pressure? 110. So that's together called the STP. You can do a calculation. At STP, what is the volume for 1 mole ideal gas? 22.4 liters. So then, if you memorize that number, then you can just you can simplify a lot of calculations. But all those information is kind of like it's very similar. So what is important are those like your conceptual plan or your strategy, right? Your strategy, for all those different ways to get the mole is mole A to mole B, right? And in this chapter we say we get mole of something from those gas law, right? And then we can use mole of something gas to get the volume temperatures. And you also review like what you learn. Like, if you have a solution, you get more from molality. If you have a pure solid, and you use like the mole mass and a gram to get the mole. All right. I think that's you seem to have those like a concept in your mind. Right? Right, so now let's do like some little practice. So we have this example, let's see what this has. What volume in liter of hydrogen gas at a temperature of 355 Kelvin and a pressure of 738 meters mercury is required to synthesize 35.7 grams of methanol, and methanol can be synthesized from hydrogen gas and carbon monoxide gas from this equation. And this equation is a balance. As you emphasize, you must have a balanced equation to do those kind of calculations. Right? So what you want to find out, let's again go in like the backward way. You want to find out the volume of hydrogen gas. Right? Hydrogen gas is H2 gas. You want to find the weight. Right? So obviously this is about the gas problem. Gas problem is about those gas law. Right? Gas law is about like the Boyle's law, right? Charles law, and ideal gas law. Right? So I think after you like read the question carefully, do you know like those different pressure, two pressure for like the hydrogen gas? We don't have two pressure for the hydrogen gas. We have two temperature for the hydrogen gas. We don't have that. Therefore, what you think about is that ideal gas law, not those Boyle's law or Charles law. Understand? But that equation has a volume in it. Why I think about that? Because that equation has a volume in it. Okay? So we start from this. That is what you want to find out. You want to find this. Okay? So that's the usual way to solve the problem. Just see what you want to find out. Then you will think about who or what is connected to what you want to find out. You want to find the mass. You think about what has to do with mass, density, molarity, mole, and all those has something to do with mass. Right? You want to find the volume. So you think about what has to do with volume. Well, density has volume in it. Right? Molarity has volume in it, and obviously this is about gas. Therefore, you're going to use gas law. And gas law that PV equal to nRT has a volume in it. Right? If you want to use this equation and find out volume, right? What else do we need to know? We need to know the pressure. Right? For that particular gas. What kind of gas we are talking about? H2 gas. Do we know the hydrogen gas pressure for in this problem? That is that, right? Do we know the temperature for the hydrogen gas? Now in this problem we don't have those gas mixture problems. So even though probably you will produce a gas mixture, but you just want to calculate how much volume of those pure H2 gas. And obviously in the reactions you are mixing all those together, you will have those gas mixture, right? But the question is ask you what volume of pure H2 gas do you need? Therefore, you don't have to worry about what part of pressure for those. Just the pressure given to you is that pressure. Under that pressure, what will be your volume of H2 gas? So therefore, that pressure is only for the H2 gas. All right. So analyze those problems. We say this one is given. Right. So that's like that. We have that millimeter mercury. Right. And this one is our question mark. This is something you want to find out. Okay? Yeah, you want to find that out. That your outermost problem. You think about it, or you find out all the other problems and come back and put into the equation to solve that. Right? So do we know the R? Yeah, so R is 0.08206. Do we know the temperature? 355 K. Right? So what else do we need to find out to solve the problem? The mole. Right? The mole of what? Mole of you can use mole of methanol. Very good. Okay. Right now we are on this step. Okay? We are at this problem, so we want to find out the mole of H2. Once you find the mole of H2, you know the temperature of this H2 gas, you know the pressure of H2 gas, then can solve this equation for the volume of H2 gas. Okay? Very good. Now how can you find the number of H2? You see like what are the information you have about the problem, right? How can we find out the number of H2? Use more ratios. Right? Use more ratio between H2 and what? And methanol? Very good. We will get N, okay, H2 from the more ratio of H2 acid to this H3OH. And this more ratio, let's see, what is the more ratio of this two guys? How many? Let me read this. I saw this. I saw it like that first. More of. So that's more of CH3OH. I think I run this one, but I think we are going to use this one, right? So we want to get the more ratio. That means you can write out the more of something with more of something else, right? We can call this A, that is B, but if you have the real substance, just use the name, whatever you have, right? So what number do we use for the more of H2 and the more of methanol? No, this is methanol. This is called methanol, right? So this is called methanol, right? It will taste, smell like the alcohol. I think in the forbidden period, like some people are drinking that. What? We have that 2 and 1. So obviously this is only the ratio. You want to get the more of H2, right? You get the more of H2. Right? To use this ratio, and obviously you need to know some other information, right? So what else now? What do we need to know to find out more of H2? More of methanol, right? Or we'll go back to our chapter 1, chapter 2, right? So we need to know more of CH3OH. And put some blank here, right? So if we can find out from the given information of this problem what is more of methanol, then we will use this more ratio to find out more of H2, and then we'll do like forward more of H2. H2 will put into this equation and we'll solve that for this volume. Right. So how can we find out more of methanol from those given information for this problem? Do we know anything about the methanol? Yeah, so it's kind of like switching your mind, right? So you see like what you will find out is about H2, right? But some other information is about something else. Some information is about H2, right? But some other information is about methanol. Now that is what the purpose of the chemical reaction equation. The chemical reaction equation can convert. So that kind of like it do something for you. The chemical reaction converts H2 into methanol, so then you do the calculation. You will just convert it between the H2 and methanol, right? All right. So we are going to use in our what we learned in chapter 1, chapter 2. You have this gram of methanol CH3OH, right? And again, this process will be very, very easy process for us now. And you just see what will be our, what is the number? So then 1 more of CH3OH. Right, so here is the 1 CH3OH. You see that? Good. So then this gram and gram can out, and you will get how much more, right? Right. Okay, so calculation, 35.7 divided by 32. Maybe what is that, 32.2? 0.04? 0.04? Okay, so get 1.11. I think that's good. So that will be CH3OH. Okay. Now we have a number here now. So let me erase this and put the number here. So here we have this 1.11. Right? Okay, now you see the calculation, the more marginal the unit comes out, right? And you will take 1.11 and multiply by this more ratio, which is 2 or 1, you will get 2.2 and 2. Now the unit is different, it becomes different more of these two. Right, so now pretty much that becomes the same now. You will just right, and one thing we need to do is before we really put it into that equation, we have to convert this pressure, right? So how you convert this millimeter mercury into what? Into ATM. How you convert the millimeter mercury into ATM? Yeah, so you know that equation, every 1 ATM is 760 mmHg. So these two comes out, and let's write like that. 738 divided by 760, that gives you 0.971. Okay, what was the question? What do we do next? It's pretty much next you just do the substitution, right? Alright, I think we have what we need ready, right? And we have the pressure 0.971 here, right? And volume we don't know. Do we know the mole of our gas? Which is 2.22, right? And R you should be able, I think the R, probably on the final exam there's a table or some of those common constant, if it gives you the R, this number, but there's some other number for R, you should know what R you're going to use. Right? So when you talk about those pressure and the liters, and you heard use this number, when you talk about those energy like joules, you use another number. Alright, so our temperature is already in kelvins, you put everything in. Right? And that's what we very straightforward, right? So your volume will equals this number divided by 0.971 and 0.971, so these two cancel out. Alright, so volume equals those numbers and multiply and divide. You should get a very similar number. I think you can see like our more is different like all because we get that we running very early, right? So we'll get probably we'll get a different number for the volume, but that's probably like close enough. But you have that. Right. Always do the same. So I think what I prefer for most of the program is going like a backward. Yeah? And for this program, you think about what you want to find out. You want to find out like a gram of Ag2O. So I think about Ag2O gram. How can I get a gram? Gram I can get from what? I can get from gram is mass. I can get it from density. I can get it from volume, depending on what you know, right? so what do we find out? What do we get?
Eight.
A?
No?
I think yeah, it's definitely A.
You don't have.
I usually probably C, but not C. Right, any questions? So what you did, how you get A? Anyone want to come here and write out how you get A? Anyone in here? I got this. Anyone in here want to write out your result? So you get A, maybe? I thought, yeah, you get, huh? Okay. Okay, let's see how you solve the problem. You want to get the gram of AE2O, right? So what do you see? You want to get the gram of AE2O, then you want to get what you want to get. How can you get the gram of AE2O? You get more, right? Yeah. Then how can you get more of AE2O? All the information about something else, right? All those drawing. Okay. You explain like from the beginning, step by step, how you do it.
Oh, I just did the PV equals nRT. So you had to convert the millimeters of mercury to atmosphere, so you have to divide by 760. And then
For the pressure,
for
right?
the pressure, so you plug that in for your P, your volume was given. You're looking for moles, your R, your temperature, in Kelvin already. So you solve for N and get 0.1 moles of O2, and then you use the equation from, mole ratio from the equation given. So you want to find Ag2O, so you have 2 moles of that over 1 mole of the oxygen, and then you get 0.2 moles of the Ag2O, and then you use the molar mass of Ag2O to get grams.
Any questions? No question? It's a very interesting type of problems. Okay? So that's the typical conversion about the chemical reactions. And the chemical reaction you can convert, then you can do the calculations. So in these problems, most of the information given to you is about O2, right? So the volume is O2 gas, okay? And the pressure is about the O2 gas, temperature is about the O2 gas, and from those information about those gas, you think about those is gas law, right? So gas law, you can use different gas law, and just analyze what kind of gas law you can use. Can you use Bohr's law? Can you use Charles' law, right? You don't have like 2 temperature, 2 pressure, think about use ideal. Well, at least you get those ideas. You get the gas value. So therefore, what Michelle did and Don did here is use the ideal gas equation to get the mole of the O2. But the question is about mass gram of Ag2O. Alright, so that's, as I said again, it's a typical calculation about those chemical reaction equations. Usually will give you something, maybe give you some gas, right? Or maybe give you some solids. You want to convert into something else. What you use, the important step is this guy. Right? What is this? What is 2 mole Ag2O over 1 mole O2? What is that, crystal? You got crystal, right? The mole ratio, right? Mole ratio. So this line is the mole ratio, right? That is a very important step. The mole ratio is a very important step. All right. Any questions? Right. I think one more example, one more practice. How many gram water form when 1.24 liters of hydrogen gas, H2 gas, at STP completely react with O2? That means we have enough O2 to use up all this 1.24 liters of hydrogen gas. Then ask you the gram of H2O. So what do you do? So when you see the chemical equation, that means it's about conversion from something to something else, right? You want to get the gram. So if you think about it, you want to get the gram of H2O. What you want to know is more of H2O. Now how can you get more of H2O? Well, again, different way. If you have the gram of H2O, you divide by the molar mass. If you know the something else, if H2 is a gas, if you know the pressure, temperature, you get that, right? But this, you probably want to get the mole from the mole of H2, from H2, right? All right. So that's our conceptual plan, right? All right. So what do we do? Just do the reverse. We'll get, so this will be the mole, right? The mole. And, well, to finish this problem, you will see that you can get the mole of H2 from the volume of H2. Okay? Now let's completely going forward. Okay? So that means going this way. Okay? So we're starting from this guy, okay? Go all the way there to the gram of H2O. Okay, what volume do we know about H2? 1.24 liters of H2. And this is at what condition? At what temperature, what pressure? STP. Now at STP, there's one very important equation. Is 1 mole equals how many liters? There's a connection, right? So there's a 22.4 liters. Right. So this will be our first equation you want to use, the first conversion. Right. Again, you think about, you want to find out what equation or what formula has something you want to find out. Obviously, you still can think about PV equals N, R, and T. You can think about that either, right? Also, you think about it also, but that will give you the same result. That will give you more calculations. Right, so you have 22.4 liters and H2, and then you will have 1 mole of H2. Understand? Okay, now you will see the conservation. So this liter and liter come out. So right now we have the mole of H2. Right? So what do we do next? So this is our first step. We finish our first step. Right? So now we have the mole of H2. So that's our first step. Our first step is using this fraction. Right? what do we do our second step? Very good, more ratio. Right now you have more of 82, and you want to get more of 82, you need to count out. More of 82 is what you want to get, right? So you can go in like that, right? So now how you get those numbers? You get those numbers like how many more, like one more, you see like those, or use the model method, always one more, right? You can get those number more by use like the capital M molarities, that depends on how much molarity you have, right? Now for those more ratios, you get the more ratios, those numbers from what? From the coefficient, and the equation must be balanced, right? If this equation balanced, that's balanced, right? So therefore, what will be the number for the more of 82? Yeah, and the more of 82. Again, where we get these two? From these two, right? Where we get these two? From these two, right? Yeah. So even though both are two, but you know where you get which one. Alright, now let's see the calculations. Let me change the pen again. More of 82, more of 82 come out. So this is our second step. Right? Now our last step. Right, so let's call that our number 3. What do we do with number 3? Model mass. Okay? So we will multiply. Okay? So this was our number 3 step. Model mass of what? 82. Because right now you know the more of 82, okay? And you want to find the gram of 82. Okay? But model mass of 82 or model mass of medicine or whatever those compound or element, and you should be able to find that out. And you also know like in that model mass, that more is always 1 more. Right? Right? So therefore you will see that you want to put this more of 82 here, okay? Because this one will come from our molar mass, and then therefore this number will be 1. So even though in the coefficient, I mean in the balance equation you have this 2 here, but you already use that 2 information. You already put this 2 here, right? So therefore for this part, this comes from the molar mass, you don't like reuse that 2. Right? And you know how to get the molar mass of 82 will be 18.02 gram of 82. Right? Now let's see what will come out. What will come out? What will come out? So you get a 997, which is a gram. See this more water comes out with that more water. And then the only unit left over is a gram of 82. Any questions? Okay, now let's do a practice, right? Let's do a practice. Let's do a practice. So you can do either way. So now you want to find out. How many liters of oxygen gas at STP required to produce 18.5 grams of H2O. Okay, so let's see. We want to find out. and now divided by 2. And then equal times 24. So yes.
Well, I was gonna do tomorrow off for
Right. Okay, so that's about those CRE. I think the purpose of one was CRE. We talk about those property of gas, and so you know, like some of those common property, don't like forget some of those very easy problems. See, the gas will completely fill their containers, and take the shape of their containers, and their density is low, much less than solid and liquid. They are compressible, and so when you have a mixture of gas, always produce so-called homogeneous, they are fluid. Right. So then to understanding this few property of gas, you can use one theory called the kinetic molecular theory. In this theory, there are some of those major assumptions. So one assumption is assuming like those particles in the gas are constantly moving, they are always moving. So even though that maybe not always true, because when they gliding, they probably just gliding like kind of head on, they will stop for a while, but then again they will become moving again. So then the attraction between the particles in the negligible, that's also an assumption. And so most of the time they are true, because they are those kind of molecules, under those conditions, their relative attraction is negligible. And there's also a lot of empty space, and so then one very important assumption is the average kinetic energy of those particles is directly proportional to the temperature in kelvins. Right? And as we learned before, we know when you have a gas mixture, like the air has oxygen gas and N2 gas, and obviously we don't have one temperature. So therefore, the average kinetic energy for all those components are the same. And then you know that the formula for the kinetic energy is Ke equals the mass times speed or velocity squared. We sometimes use different letters to represent velocity or speed, right? So therefore, even though at the same mixture, you have the same temperature, so therefore this will be the same. Okay? It's very similar as that Boyle's law, right? So Boyle's law is the P times V equals constant. On this guy, if you specify the temperature is constant, okay? So therefore that is constant. Okay? So the pressure times volume when the temperature is constant, that's also constant. And that's two inversely proportional, which means if your pressure increases, the volume decreases. And similar here. Okay? And for those different gas particles, different gas like the oxygen and nitrogen, you have different mass, so obviously you have different average speed. Okay? So that is one thing you probably want to you want to know. So different gas will have a different average speed. Okay? And then even for the same gas, okay? And you will have an average speed, and then when you have gas, have like a collection of gas, you have like gas particle number 1, particle number 2, you will have like Avogadro number like 1,000, 2,000, those kind of gas like in your gas mixture. So then each gas don't think that they always moving with the same speed. So some of them moving faster, some of them moving slower. You will have an average. And then those average, if you have a gas mixture, and depending on what mass they have, you will have different average. It's very interesting, like those observations. So now, if you remember something what I said, you will be able to find out this answer for this CRE. We have 4 most common gas in the atmosphere: N2, O2, argon, and CO2. Then the question is, which has the highest average kinetic energy at room temperature? They all have the same temperature because they all in the room have the same temperature. So therefore, they all have the same temperature. So that's about it. So then what I talk about that is velocity or speed. So let me just for 5 minutes think about. So that so I said the average will be different if you have like in the rooms and then also very interesting important thing about that is for the same gas as you have pure hydrogen gas or pure oxygen gas, if you specify the temperature, therefore you specify like the average kinetic energy, okay? But don't be like thinking, don't like get a wrong concept. You have the average kinetic energy. That average is average. Very similar. You have like 5 quiz. That means you have the same score for all the quiz. Okay. So therefore, those kinetic energy or the speed for different particles will be different. Okay. And vice versa, you will see what is the percentage, what are the fraction of those particle has some speed, and you will not have like only one line, have this curve. So then how you take the average? I think that just want to know that you have different ways to take the average. So this one way of average is different, like different than your usual average. If you have like 3 quiz, so you think about you have three quiz. I think you have 10 and 11 and 12 scores. Your usual average will be this 3 plus and divided by 3, you get 11. Right? Now, what we do the average for the average speed, in different ways. What we do is you just take the speed of each molecular or each atom and square them. And then add them together. Not only take those 10 plus 11, you will take 10 square plus 11 square plus 12, 13 square. Then divide by 3, then you take the square root. So those areas little different, you will get a little different result, but usually that not make sense to us because you don't do those kind of calculations. So why we use that? If I have time, I'll tell you why we use that. That's because later on. Now, let's say you have those different gas at the same temperature. Okay? So I said at the same, if you have a gas at the same temperature, that means you probably have a mixture. Then you will see the speed. Okay? Their average speed will be different because at the same temperature they have the same average KE. In order to get the same average KE, because they have a different mass, so you have that formula, and m times v squared, right? So if they have a different mass, so you want to get the same number altogether for these to multiply this or square, then this one is different. Okay? So now we can see those two curves were different. All right. So then, and here is why you will use that square. I mean, use that average. Okay? So what you do? How you take the average like that? Okay? And how you get the average of the KD? You think about it very similar as you do the quiz. So you will see like what is the KE for one particle? Let's see, we call that 1, 2, 3, and blah blah blah. And here we get that Avogadro number, right? So this is one atom, or maybe one molecule like that. Right? So each of them has a KE. Each of them have that speed. You will call this is V1, this is V2, this is V3, this is Vn, Vna, right? So each of them have their like speed, and all of them have the same mass. If you talk about one particular atom, maybe helium, maybe argon, they all have the same mass, but they have a different speed according to the Boltzmann's something, right? So now, what is the KEI for this one? Or V1 squared, right, for the first one. What will be the KE for the second particle? What is the KE for the number 3 particle? With 3 squared. And then what will be the last one? Now you can take your usual average, right? So you have the KE for the first one, this number, for the KE for the second one, that number. So you do your usual average. Yes, this plus this, this plus this, plus. Okay. adding all together, well, how you do the average for your three quiz? You're adding all the 3 divided by 3. If you have that Avogadro number, you will divide by the Avogadro number. Now that will give you the average PE for one particle. And you see all those numbers, all those terms here has 1 over 2 times n, 1 over 2 times n. Okay? What you can do is 1 over 2 times n, and just write that in front. Right? Then what you left over is v1 squared plus v2 squared. Right? And then plus blah blah blah, and v and v squared. Then divided by n. What do you call this guy? Well, this guy, you give them different letters. You can call them v anymore. You call them u. You got a u squared. Then this bar means average. So you almost there get that equation. What you get right now, that means you will have that half m u square bar. And this is the average KE for one particle. You want to calculate the average KE for one mole, you just multiply that by the Avogadro number, because Avogadro number is in 1 mole. And that will give you this equation. Right? So that's pretty much about this chapter. And then you combine that together with the other equation, you get that formula to calculate that URMS. You don't have to worry about that. So then you have two different processes called effusion and diffusion. I think you should understand. Diffusion, like if you like draw 1 ink of milk in water, you will see that gradually it will disappear. That's called the diffusion. Effusion is like what this figure tells you. And those rates, for those rates, that's proportional to that molar mass, 1 over molar mass square root. So then the last slide is about the Greenham's law is about the rate of effusion. If you want to compare the effusion of 2 different gases, let's say gas A and gas B, and you have that formula. For example, you have 2 different gases. You see this balloon, I just add on like this is helium, and that what is that? That's argon. And so those are the molar mass will be different. So then from that equation, you will see which gas will disappear quicker, which balloon will get flatter quicker. That's helium, because why is helium? But that equation tells you, okay, if you put that rate of helium, you see this rate of helium over rate of argon, that means there is diffusion rate. Okay, so the ratio rate that will equal square root over the molar mass of argon. Molar mass of argon is about, what is molar mass of argon? 40? 39? And then what is molar mass of helium? The 4 is more larger than 1, right? So you take the square root is still larger than 1, which means the rate of effusion of helium will be larger than the rate of effusion of argon, which means the balloon of helium that filled with helium will become like empty first. So that is about gas law. And so let's do traditional lab. Traditional lab is relatively easy. You just first go there and get the aluminum can, cut it and put it in the beaker, put it into the food, and you heat it for 30 minutes. And right. Don't forget, I think we'll have a quiz online to do like this, right?
Oh, you already finished it?
Probably want to put the
see if you can do that. See if you can do it. Let's do
Satchel.
Yeah.
Oh, okay.
Hey, you guys want that? Probably good idea.
We start on the field one, right?
Yeah. Where other guy? Where's the other guy?
You think you know where they are this?
You would think I would know his name.
Hey.
You're a good guy.
Just with her.